All right, so when we defined our line integral previously, we had defined it with respect to arc length. You know it's with respect to arc length because the differential in your integral is a ds. But there are other useful ways of defining a line integral by choosing a different differential. So what I'm going to do, I'm going to refer back to this picture right here. When we defined our line integral as the limit of this Riemann sum as n goes to infinity, these delta si's corresponded to the length of each individual subarc. However, if instead of putting a delta si here, if we put a delta x or a delta y, or a delta xi or a delta yi, what we would mean by that is the change in the x coordinates only or the y coordinates only as we go from one point to the next along the subintervals that we broke, the subarcs that we broke this curve into. So delta xi for this subinterval right here, for example, would represent the change in x from this point to this point, whereas the delta yi would represent the change in y from this point to this point. Now, those are different quantities than the delta si. So if we define a line integral using those different delta xi or delta yi's, the end result is not going to be the same thing as what we got here, but the interpretation of those line integrals are going to end up being useful in their own way later on. So it's an alternative definition. Actually, that's probably not even the best way to say it, because saying alternative definition makes it sound like it's the same thing. It's a different type of line integral over the same curve with the same function. Those give us the following Riemann sums leading to the following integrals. Notice the difference in the notation. The only thing that's different between these two and our original line integral is the presence of a dx or a dy instead of a ds here. That tells me that I'm integrating with respect to x or with respect to y. Now, the way that we handle those types of integrals, I'm going to jump down to this little box here, is, for example, if I'm integrating with respect to x, then I'm still substituting x of t and y of t in for the x and y here, but dx becomes x prime of t dt. And we could walk through a derivation showing how that would occur, but it's very similar to what we did previously. This x prime of t dt is taking the place of that big square root that we were seeing in the ds previously. So these tend to be a little less cumbersome to work with. And I'm going to jump up here for a minute. As we're going to see later, oftentimes you're not just integrating with respect to x or with respect to y independently. You're integrating with respect to both simultaneously. So in that case, we use this notation. If I have the line integral of p with respect to x and q with respect to y over this integral c, where you see this plus here, what this means is that I'm doing each of these line integrals separately, this one with respect to x, this one with respect to y, and then summing the results. But we oftentimes will use this notation where the integral symbol only shows up once, and then you have one function dx plus another function dy. Right now, I'm not giving much motivation for why integrals like this exist, why we define an integral this way. We're going to make those connections later. Right now, we just need to know how to evaluate these. So we'll do an example with that in a minute, but I'm also going to talk about something that comes up a lot throughout this chapter, something called the piecewise smooth curve. So if you have a curve C, and it's a union of smooth curves, C1, C2 through Cn, where the terminal point of Ci is the same as the initial point of Ci plus 1. That means the terminal point of one of these curves coincides with the initial point of the other, connecting them. Then we refer to C as a piecewise smooth curve, and we define the line integral along C as the sum of the line integrals along each of those individual pieces of that curve. Okay, so I want to show an example where we're evaluating a line integral along a piecewise smooth curve. In this case, and this is also going to be a line integral with respect to x and y simultaneously. So it's kind of like one example that covers all that stuff that we just talked about on the previous page. I'd like to evaluate this line integral, x squared with respect to x plus y squared with respect to y over this curve C. And C is a piecewise smooth curve where it says it consists of the arc of the circle x squared plus y squared equals 4 from the point 2, 0 to 0, 2, followed by the line segment from 0, 2 to 4, 3. Now, in order to do the parametrization of that line segment, we talked about that earlier in the course, but it's worth reminding ourselves of what that looks like. So for a line segment, this is just like a little reminder, we use this parametrization. R of t is equal to 1 minus t r naught, use the arrow notation here, plus t r1, where r naught is the position vector for the initial point, r1 is the position vector for the terminal point. And if we parameterize this way, t will go from 0 to 1. Okay? So we need this a lot, actually, in this chapter, because a lot of the curves that we integrate over do consist of line segments, and this is the standard parameterization for a line segment. So I'm going to sketch this first. If I look first at the arc of the circle that's being described here, here's 2, 0, here's 0, 2. So it's similar to a result that we saw before where we're integrating, or sorry, it's similar to a curve that we saw before where we're integrating over a quarter of a circle in the first quadrant. Then in addition, or after that, we have a line segment going from 0, 2 to 4, 3. So 4, 3, I'm going to just put that over here. Now I'm also going to pay attention to the orientation of these curves. Look for the words from and to. From 2, 0, 2, 0, 2. We're starting here, traveling along that quarter circle until we get to the point 0, 2. And then the line segment goes from 0, 2, making this the initial point. That's important because that's what we represent r naught with. And then 2, 4, 3. So then we're going this direction. Okay? So I'm going to call this first curve C1 and the second curve C2 because those are the two pieces that make up this piecewise smooth curve C. Before I can jump to my integral, I need parameterizations for both curves as well as x prime and y prime for each of those parameterizations. So this is a quarter of a circle oriented counterclockwise, and the radius of this circle is 2. We know that the parameterization for this would be x equals 2 cosine of t, y equals 2 sine of t, and t is going to go from 0 to pi over 2 again because we're only in the first quadrant here. I also need x prime. X prime of t would be negative 2 sine of t. Y prime of t is going to equal 2 cosine of t. Okay? I'm also going to parameterize C2. And I'm going to go down here to do the work for this. I'm using this parameterization for a line segment. So 1 minus t, I have r of t equals 1 minus t times the position vector for my initial point, which was 0, 2, plus t times the position vector for my terminal point, which was 4, 3. This, if you multiply these scalars in and then combine everything, you'll see that you get the vector 4t, what's the other one? 2 plus t. There we go. Right, yeah. Okay. So this is the x and this is the y. That means I have x equals 4t, y equals 2 plus t. And again, for these parameterizations, t goes from 0 to 1, using that standard parameterization for a line segment. X prime in this case is 4, y prime would be 1. Okay? That's the setup. Lots of setup. But now we can jump to the integration part of this. So the integral, again, the one that I'm evaluating, is over the piecewise smooth curve. It's x squared dx plus y squared dy, but I'm going to handle that in the two pieces and then sum the results. So let me start with C1. If I want to integrate C1 of x squared dx plus y squared dy, x is 2 cosine of t, and dx is negative 2 sine of t. So that's going to give me the integral. And don't forget, our limits are 0 to pi over 2. So that's going to be my limits of integration. 0 to pi over 2. This will look like, after multiplying everything, negative 8 cosine squared of t sine of t dt plus, notice I'm not going to write a second integral here. I'm going to keep this all as one integral. Y squared is equal to 4 sine squared of t times dy, which would be 2 cosine of t. That's going to give me 8 sine squared of t cosine of t dt. Okay? Now, we would evaluate this by treating this like two integrals, both from 0 to pi over 2, integral of this function plus the integral of this function. Both of these could be handled with a very straightforward u substitution. Use u equals cosine of t here, u equals sine of t here. The integration is it's not that time consuming, but it's more time consuming than I want to spend here. So I'm going to leave that part to you. This turns out to just be 0 in the end. Okay, so that means it's not going to contribute anything. Let's go to the second part of this, C2. I also need the integral of this second piece. So x squared dx plus y squared dy. This one, we integrate from 0 to 1, because again, there's our parametrization right there. X squared dx, that's going to look like 4t squared times 4. Then I have this dt here. Okay, plus y squared, this is 2 plus t squared times 1 dt. Okay, again, this, if you expand everything out, is just a polynomial, and it's not a very difficult polynomial to work with. Those are the easiest things to integrate, so I'm not going to use the time to walk through step-by-step integration with a polynomial. This one, once you integrate, comes out to 83 thirds in the end. So what this means is that our final answer, the integral of over c of x squared dx plus y squared dy, is going to equal 0 plus 83 thirds. It's the sum of the two pieces that we just found. This becomes 83 thirds. Okay, that's it for that. All right, a little bit of information just to wrap up this video, and it'll help lead into some examples that we see in the next one. So again, I've been emphasizing the orientation of these curves, and that's because if you get your orientation wrong, it changes the value of your integral. So just to be a little bit more specific about what I mean by orientation, if you have this little arrow here pointing this direction, what this means is that our curve C has been parametrized by functions of t, x of t and y of t. As t increases, the points that we get on this curve should be going this direction if our orientation is this direction. So this is pointing in the direction that this curve would be traced out as t increases. If you reverse the order of the orientation, if you reverse the orientation of a curve, so the same curve C is drawn again here, but the arrow is pointing the opposite direction. So that means as t increases, for the parametric equations that would define this curve, we would be going this direction instead of this direction. We notate that by negative c. That just means the opposite orientation for that curve. We can show, we're not going to do this here, but we could show if we went back to the definitions for these line integrals, that if you're looking at a line integral with respect to either x or y, if you change the orientation of the curve that you integrate over, then what you get is the opposite of the integral that you would have gotten if you didn't change that orientation. So this negative, you can think of it sort of as being brought out of the integral. And if you wanted to look at why that happens, it's what this does is it changes the order of subtraction whenever you evaluate a delta xi or a delta yi. Instead of xi plus 1 minus xi, that becomes xi minus xi plus 1. You get the opposite of that. Now, down here, this is where we have to be really careful. If you change the order of, if you change the orientation of a curve, but you're integrating with respect to arc length, it does not change the integral in any way. And the reason for that is because arc length is independent of orientation in that sense, where the length of one of those subarcs is the same whether you're going this direction or that direction. It does not change the value of the integral. Okay? And I think I'll cover this part in the next video.